Lesson 10-2, the real number system. We are talking about sets of numbers, and pretty much most of the time, all the things that we've dealt with rational numbers, but we've also most recently introduced things using irrational numbers, especially the most famous irrational number, which is pi. So kind of the goal today is for you to understand the difference between rational and irrational. On your I-STEP test, you will be asked which numbers are rational versus irrational. The thing is, all of these fall into the sets of real numbers. So let's see if we can tell the difference. The definition of a rational number is it can be written as a fraction or decimal. Okay? So all of the things on this side of the box, that Venn diagram, all of those are rational. And you see the sets that are inside of there, whole numbers and integers. I'm going to add one more just inside inside the whole number, which you can barely see it. Inside there, I'm going to add natural. Natural numbers are counting numbers that you first learned in kindergarten. And the difference between natural and whole is the number 0. Because whole numbers begin with 0, counting numbers begin with 1. Because you start counting with 1. So we need to add that in because when we take the quiz on Friday, we will be asked to know about natural numbers too. But natural numbers are inside the set of whole numbers. So I'm going to I should have probably added them down here, and I'm going to show you what that arrow is along the side that we've got there in just a second. So rational numbers, anything that can be written as fractions or decimals. When you identify them a lot of times, not only in what we see as our workbook page that you'll be doing for homework, but the quiz also. Usually for rational, strangely enough, we use the letter Q. We don't use R. R stands for real. Okay? So decimals, when it says decimals that are rational, decimals that end, like something like 0.5 or 0.25, those would be rational. Or if they are repeating decimals, those definitely would also be rational, because both of those kind of decimals, you can make fractions out of them. Integers and whole, kind of the same way. Both of those kinds of numbers, you can make them fractions by putting them over 1. So on the set of integers, begin with negative infinity, and then -2, -3, -2, -1, 0, 1, 2, 3, and it goes to positive infinity. And it shows you right here another strange thing, but Z is what we use to represent integers. We don't use I because I stands for irrational down here. Okay? When you do these problems, they would have the Q and the Z and all that at the top and tell you what they stand for. So you don't really have to remember those. I'm just saying, yeah, it's strange, but those letters do represent those number sets. Whole numbers are inside the set of integers because every whole number is an integer. It just doesn't have any of the negatives. So whole numbers start with 0, 1, 2, 3, and they go on ... into positive infinity. Again, you can make those a fraction by putting them over 1. Now this one makes more sense. Whole numbers, they would begin with, or they are represented by the letter W. Makes more sense. Natural would be represented by the letter N. Okay. Now over here on the side, because you're going to be given some numbers and ask what sets you think they belong to. So this arrow that goes up the side, wherever you think the number fits in, it also is in every set above it. So if you think something's an integer, it's definitely an integer and a rational. If you think something is a whole number, then it would be a whole number and an integer and a rational. Okay, so that's kind of what the Venn diagram is showing there. Anything that's in one of the circle sets, it's not just in the circle sets, but it's also in the whole set of rational. Numbers like 1/2, those are just rational. They don't fit into integers or whole or natural. 0.4, 2/3, 0.3 repeating, all of those are just rational. Okay, let's talk about irrational for a little bit, because that's more new to us. Irrational, the big thing is they're definitely decimals. They are non-terminating. That means that they don't stop. That means when you see them, you'll always see a dot, dot, dot at the end. And they are also non-repeating, okay? So if you saw something like 0.1212121212, that's repeating. But if it was something like 0.123789, you know, that is not repeating the same digits. So that's irrational. So definitely we said the most famous irrational is pi. 0.12345, notice there's dot, dot, dot. Okay, so that would be, it's not repeating the same digits. And the reason why we're talking about this in this section, in this chapter, is square roots. Many, many square root numbers are irrational. If you plug them into a calculator and they fill up the whole display, that means they don't stop, they don't repeat, they are irrational, many of them. Now don't be tricked, because if you saw a square root, don't just assume it's irrational, because what if it was square root of 25? What is that really? 5. So don't be tricked. Don't say, oh, there's a square root, it's irrational. That's not necessarily true. So you might need to evaluate that first and then decide. Okay, any questions about that diagram or that? Just kind of keep that there, because we're gonna go on to some examples, and I want you to have that to refer to, okay? I'm not going to have it up on the screen. So let's go down to what kinds of things you're going to be doing. Name all sets Q, Z, W, I, and I'm going to add N to that. Now remember, Q is rational, Z is integer, W is whole, I is irrational, and N we've added in is natural. What's the difference between natural and whole? Only one number, right? What's that number? 0. Whole numbers have 0, natural just start with 1. Okay, so let's look at this one. Negative 10.1. Negative 10.1. Which set or sets do you think negative 10.1 belongs to? Any ideas? Cece? Okay. Z, look back at Z once. Does Z have any decimals with it? The integers? No. Now I know why you said integers, because there's a negative with it, I bet, right? When you guys think integer, you think, oh, it's got the negatives too, but also it has to not have any decimals with it. So it's not Z and Q, Cece, it's just Q, because it has a decimal that stops. Okay, negative square root of 81. Negative square root of 81. Think about that for a minute and what it really is. What is negative square root of 81, Tori? Negative 9. So which sets would negative 9 fit in? Yep, Q and Z. This time it does. It's an integer because it just is a number. It's a negative 9, so that's an integer. And then integers are definitely rational, so that's a Q. Square root of 35. Now, when I evaluate square root of 35, here's what I get. 5.916 dot, dot, dot. What's that tell you about square root of 35? Trayton, what'd you say? It is irrational, so therefore we'd say I. It's a decimal, it doesn't repeat the same digits, and it goes on forever. Okay, 42 sevenths. What is 42 sevenths? 6. So the number 6, what sets would it be in? Shane, what are you thinking?
W and Z.
Definitely whole. Whole is inside integer. Anything else?
Z.
I got W and Z. Those two are also inside of, what's the big category?
What? Oh, me still?
Yeah, you still. It's definitely whole. It's a whole is an integer, and both of those sit inside which box? On the left.
I'm confused right now.
Okay, so it's not just whole and integer, it's also what, Stephen?
Q.
Q, rational. And then the one that I added, natural, is, can you count with the number 6?
Yes.
Yes, so that's why it's also N. Okay, so it's natural, whole, integer, Q. And remember that list that you had in the beginning of your notes? Whatever category it fits in, it's in everything above it. Okay, so it's in all of the ones above it. All right, next we're going to replace with less than, greater than, or equal to 5.15 repeating and the square root of 26. So what do you think you'd have to do to be able to determine this? What would be the best thing to figure out?
You'd have to take 26 and find the square root.
Yeah, the square root of 26. So when I do that, here's what I come up with. 5.09 dot dot dot. So now can we decide less than, greater than, or equal to? Yeah, you could decide by the tens place. That tens place is a 1, and that tens place is a 0. So definitely this would be greater than. So that's what you'd have to do is evaluate some of these. All right, we're also looking at ordering sets from least to greatest. So we've done this before where you have to take those numbers and divide them out or figure them out so that you can compare them by decimal. What can we do with the square root of 64? Anybody know what that is? What's the square root of 64? 8. 8 and 1/7. Okay, you would have to divide out 1/7, and I've kind of cheated for us. Here it is, 8.1428, and that continues on. Okay, the 8.14 repeating, so that's going to look like this, 8.1414, and that's going to keep going. What about 15 halves? If I divided that out, anybody know what that would be? Tori? 7.5. Okay, so let's look at those numbers. We want least to greatest, so definitely which one's first? 7.5, but we're going to write 15 halves. Okay, so I'm going to mark that one out. Now look at the 3 that remain. What's the smallest out of those? Shane?
1/7.
The what?
The 64.
The square root of 64 is next because that's just plain old 8. Okay, when we look at the last two, we've got to go all the way to the thousandths place to determine because they both are 8.14, but this one has a 2 where this one has a 1. So if I'm going least to greatest, we're going to do 8.14 repeating and then finally 8 and 1/7. So you're going to have to divide all those out or write those out with as many decimal places as you can. Okay, questions about that? We're going to look at one more thing. This is kind of from the newer standards that we had last year. Graphing radicals on a number line. And you're supposed to do this without a calculator. So do you remember our list yesterday of perfect squares? Okay, so we need to think about the square root of 50 and where the square root of 50 would fit in our list of perfect squares. Does anybody think of one? What it's close to? Stephen?
7.
7 squared, so it's between the 49 and the 64, okay? And the square root of 49 is 7, and the square root of 64 is 8, but it's way closer to which one of those? The 7. So we're going to go just right past the 7, just a little bit past the 7, and we would put a point on the line and then square root of 50. And we did that without actually using a calculator to figure that out. Okay, now, negative square root of 12. So negative 12, if you look at the number 12, it fits in between the perfect squares 9 and 16. When I square root those, it is either between negative 3 and negative 4. 12 is a little bit closer to 9, but we're going to put it right in between negative 3 and negative 4, and that would be the square root of negative 12.